Okay, so greetings, welcome to this class. So in today's class we are going to look at analysis of braking response. Okay, so we have been looking at the brake system, its operation and so on, and we looked at anti-lock brake systems and what is the concept, how they work in a broad sense, right. So today we come to the analysis part. So if we look at the braking process itself, what analysis can be used to characterize the vehicle braking process, right. So that's something we will look at. So we are going to consider a free body diagram, which you will see that it's pretty similar to what we considered during analysis of the powertrain. So if we recall the analysis that we did for calculating the gear ratios or getting the basic equations during the drive motion, right. When we did powertrain analysis, we considered a similar free body diagram. So if you recall, we considered that the vehicle was moving up a grade of angle theta s, right, and the vehicle's weight is W. So and the wheelbase is capital L, the CG is located at a distance of L1 from the front wheel center and L2 from the rear wheel center. WF and WR are the normal loads at the front and the rear wheels respectively. RA is the aerodynamic drag, RD is the drawbar pull, RRF and RRR indicate the rolling resistance at the front and the rear wheels respectively. Okay, so all these are quantities we have already looked at. Now what are the main differences between this free body diagram and the one that we looked at when we did powertrain analysis? Please note that in this case we are applying a braking force rather than a drive force. So we can immediately observe that there is a braking force FBF acting at the front tire rod interface and FBR that is acting at the rear tire rod interface, right. So those are the braking forces that act on the wheels. Now A for us is the deceleration. So that is why it has been marked in this direction opposite to that of the motion. We consider A to be the deceleration, and consequently the D'Alembert's force, which is nothing but m times A, which we mark at the CG, and in a direction opposite to that of the deceleration, that's going to be W by G times A, right. That's the D'Alembert's force. Okay. So what to say, the weight of the vehicle is W, and that's going to be resolved into two components, W cos theta s perpendicular to the road and W sin theta s along the longitudinal direction, right. So those are the various forces acting on the vehicle. So the main differences are the presence of a braking force rather than a drive force at the tire rod interface, and the deceleration is now the other way around, right, and the vehicle is being decelerated, and consequently the D'Alembert's force W by G times A is in this direction. Okay, so those are the main changes. So let us consider the free body diagram of the vehicle during braking. So as we just discussed, FBF and FBR indicate the braking force at the front and rear wheels respectively. Now if we balance the forces, right, along the longitudinal direction, so balancing the forces along the longitudinal direction, we obtain in this particular case, so W by G times A, that is nothing but m times A, that is going to be equal to FBF plus FBR plus RRF plus RRR, which are the rolling resistances, plus RA plus RD plus or minus W sin theta S. So, if you recall when we did powertrain analysis, aerodynamic drag, draw bar pull, grade resistance and also rolling resistance were called loads, because those had to be overcome by the drive force. In this case, please note that these are resistive forces anyway, right. So, they aid in the deceleration process, right. So, that is one important difference. So, FBF plus FBR is the total braking force FB, which we are denoting by F subscript B. This, as we already know, is the total rolling resistance R subscript R, which we can rewrite as FR times W, FR being the rolling resistance coefficient. So, we are aware of these aspects, right. So, consequently, what will happen is that FB plus FRW, that is going to be equal to W by GA minus RA minus RD minus plus W sin theta S. So, I am just rearranging the terms, right, of this. So, let us call this as some equation 1, right. Okay. So, now what is the next step that we would do, like let us say we call these points of contact, like as A and B respectively, that is where the center of the front tire rod contact as A and the rear one as B. So, we take moments about these 2 points. Okay. So, taking moments about point B, or balancing the moments about point B, right, we obtain the following. So, we can immediately see that WF times L is a clockwise torque, and then we have RAHA is another clockwise torque, plus RDHT is another clockwise torque, plus or minus W sin theta S times H is another clockwise torque, right. These are torques which are acting in the clockwise direction about when we take moments about point B. Then we balance the them with the counterclockwise torque. So, those are going to be W by G A times H, then we will get W cos theta S L2, right. So, this is what we will get. So, we assume once again theta S to be small such that cos theta S is almost 1. We assume this values of HA, HT to be almost equal to H. Then what do we get? This results in WF being equal to WL2 by L plus, if we simplify and take terms to the same side, we are going to get W by GA minus RA minus RD minus plus W sin theta S times H by L. Okay. So, just rearranging the terms, right. So, we have already done a similar analysis before. So, this is pretty straightforward, right. So, what is the term within the square bracket from equation 1? This is nothing but FB plus FRW, right. Okay. So, this implies that WF is going to be equal to WL2 by L plus FB plus FRW times H by L. So, this is equation 2. Okay. So, this is the load on the front wheel. So, once again, if we recall the analysis that we did before, please note that the static load on the front wheel is going to be WL2 by L, right. So, because if assume that the vehicle is parked on a flat road, it is stationary. So, then WF is going to be WL2 by L, right. So, this component is now the longitudinal dynamic load transfer during braking. Okay, that is a component of the longitudinal dynamic load transfer, right. So, during the process of braking. So, during braking, please note that we are going to have load transfer from rear to front, right, as we will observe shortly even from the equations. So, we can see that the load on the front wheels is going to increase, right. So, that is what we can observe from here. Now, similarly, taking moments about point A and simplifying. So, this I am going to leave it as an exercise because we have already done this process, right, for the other wheel, right. So, if you do the same process and make the same assumptions, cos theta s is almost 1, HA, HT almost being equal to H and so on. So, and then like use equation 1. So, what we will ultimately get is that like we will get an equation for W R, which is going to be W L1 by L minus FB plus FRW times H by L. Okay. Let us call this as equation 3. So, this I leave it to you as an exercise, right. It is pretty straightforward, right. So, you will get this one. So, immediately we can observe that W L1 by L is the static load and FB plus FRW times H by L is the dynamic load transfer, right, during braking from the rear wheels, right. Please note that during acceleration there is a dynamic load transfer along the longitudinal direction from the front to the rear. Now, during braking it is the other way around, there is a dynamic load transfer along the longitudinal direction from the rear wheels to the front wheels. So, we can see that the same quantity is being subtracted from the rear and added to the front. Okay. So, that is what is happening during braking. Okay. So, this is something which we can observe. Now, we move forward and then like we look at what will be the maximum braking force that one can obtain at the front and the rear wheel, right. So, when we did powertrain analysis, typically we reasoned out that in a typical road vehicle either the front wheels or the rear wheels are driven. So, we looked at front wheel drive and rear wheel drive and derived expressions for the corresponding tractive forces, right. But in a typical road vehicle all wheels are braked. Okay. So, friction brakes are installed on all the 4 wheels in a 4-wheel vehicle. So, we have to look at what is called as brake force distribution, okay, between the front and the rear. So, let us look at that important concept. Okay. So, to analyze that, let mu p be the peak friction coefficient, okay, at the tire rod interface. Let us say this is same for all the 4 wheels, without loss of generality right now, right. Let us assume that it is the same, right. So, let mu p be the peak friction coefficient at the tire rod interface. Then what happens is that the maximum brake force the total brake force, right. So, FB is, so it is going to be FB max, that is going to be equal to mu p times W. So, this is the maximum brake force that we can expect, right, because the weight of the vehicle is W. So, mu p times W gives me a numerical upper bound on the maximum brake force that we can apply on that vehicle, right. So, that is what is sustainable at the tire rod interface, right, totally. So, now the question is that how do we distribute this between the front and the rear. So, let us say once again taking a round number just for the sake of argument, let us say this maximum brake force FB max comes to be 100 newtons. Now the question is that, like, out of this 100 newtons, how many newtons should I ask the front brake to deliver and how much should the rear brake deliver? No, that is what is called as brake force distribution. So let us analyze that. So the maximum brake force from the front wheels is FBF max, that is going to be equal to mu p times WF, then we substitute the expression for WF, that is going to be equal to WL2 by L plus FB max plus FRW times H by L, right. So the only difference I am making is that, like, rather than FB, I am using FB max. How did I get this equation? From equation 2 for WF, right. So we just derived it, right. So if you look at equation 2 above, for FB I am just substituting FB max because we are interested in the maximum braking force, right. So this is FB max. FB max, as we already just saw, it is going to be mu p times W, right. So from the above equation. So this will give us FBF max will be, if we simplify this, we just take W out and then capital L out, we are going to get L2 plus H times mu p plus Fr. So that is what we will get. So this is the maximum brake force that can be obtained from the front wheels, right. Similarly, the maximum braking force of course, this should be maximum brake force from the front wheels, right. So similarly, the maximum brake force from the rear wheels is FBR max is going to be equal to mu p times WR, that is going to be equal to just the same process, it is going to be mu p WL1 by L minus FB max plus FRW times H by L. So once again, this FB max is nothing but mu p times W. If we substitute, we get the final expression. So this implies that FBR max is going to be equal to mu p times W by L times L1 minus H times mu p plus Fr. Okay, so this is the maximum brake force at the rear wheels. Okay, so then we define what is called as the ideal brake force distribution. Okay, the term ideal brake force distribution. Brake force distribution is typically abbreviated as BFD. Okay, BFD stands for brake force distribution. Okay. So what is this ideal brake force distribution? So it is that distribution of the total brake force right, that distribution of course between the front and rear wheels of the total brake force that results in the maximum brake force on all wheels at the same time. Okay, so this is what is called as ideal brake force distribution. Okay. So, it is that distribution of the brake force, total braking force between the front and the rear, that will result in the maximum brake force at all wheels at the same time. So, that means that in essence we are utilizing the traction that is available at each tire road interface to the best extent possible. That means that we are going to get the highest stable deceleration, right, because if we are essentially using the maximum friction which is available at a particular tire road interface, I am getting the best out of my brake system, right, when I am braking for a given tire road interface, right. So, that means that that is the max, that is indicator of the maximum stable braking force that I can achieve. So, consequently that will give me the maximum stable deceleration, right. So, that is what is called as the ideal brake force distribution. So, that is obtained by, we just divide the two expressions. So, essentially what we do is that we essentially have FBF max by FBR max. If we divide it, what will happen is that we will get L2 plus H times mu P plus Fr divided by L1 plus L1 minus H times mu P plus Fr. Okay, so this is the ideal brake force distribution. So, some people will express it as a ratio of two parameters KBF and KBR. So, KBF is nothing but FBF by FB, it is just a proportion of the brake force on the front and the rear. Okay. KBR is once again a proportion. What is the proportion of the total brake force on the rear, right. So, this implies that KBF plus KBR it sums to 1. Okay. So, typically for a given vehicle, you know, like if you are given L1, L2, H, mu P and Fr, you can calculate the ratio of KBF and KBR. Then how do you get the individual values? You use the second equation, which is KBF plus KBR equals 1, right, because from this equation you can only get the ratio of KBF and KBR. You use the second equation KBF plus KBR equals 1 to calculate the individual values of KBF and KBR. So, what does this mean? If someone says we are having a 70-30 front rear BFD, okay, this is an example, okay, they are essentially implying that the value of KBF is 0.7, okay, KBR is 0.3, okay, so that is the implication. So, if someone says, you know, like the BFD is 70-30 on the front and the rear, so that means the value of KBF is 0.7, the value of KBR is 0.3, okay, so that is how we should interpret it, okay. So, immediately we can observe that, note that the ideal BFD depends on the CG location, because you can observe that in the equation we have L1, L2, H, right. So, that is going to affect the ideal brake force distribution. It is dependent on the maximum friction coefficient mu P and to a lesser extent rolling distance coefficient. Okay. So, because relatively this value is going to be smaller and so its impact on this aspect is going to be lower. Okay. The impact of rolling distance coefficient on this what to say calculation of ideal BFD is going to be relatively small compared to the first two aspects. So, why are these important? First thing, let us say we even take a passenger car, let us say the mass distribution in the passenger car remains more or less the same. So, let us say we, for the sake of argument, we say that the CG location remains pretty much the same. So, immediately you observe that as a designer, as a vehicle designer, I may design my brake system for the fully loaded car, traveling on a nice dry road surface, right. So, I will assume the best possible value of mu p, okay, and let us say I calculate the brake force distribution as, let us say, some 70-30 front and rear. Suppose let us say it rains, the roads become wet, the value of mu p reduces, and I use the same expression for the same car, right, the number will be maybe 65-35. Suppose the roads become icy, the mu p drops even further, then the ideal brake force distribution may become 60-40. So, I am sure you get the point, right. So, essentially this ideal brake force distribution keeps on changing, but we only have one brake system, right. So, then what do we do, right. So, that is where active braking control becomes important, right, because even if I want the same brake force, the way I distribute the brake force between the front and the rear is dependent on the vehicle operating conditions, okay. So, that is one aspect. Second aspect is that let us say we take for example a truck, let us say that weighs around like let us say 16 tons and it is carrying sand to a construction site, it dumps the sand and comes back, it may weigh around 4.5 tons. So, from 16 tons it is going to 4.5 tons. So, then what is going to happen is that the value of L1, L2H will change drastically, right, for the empty truck as opposed to the fully laden truck. So, even though mu p were the same, now the kbf kbr for the unladen truck will be different, right, but once again we have the same brake hardware, right. So, that is where this control of braking becomes very critical, right. So, with different operating conditions, right. So, we have to be aware that there are interesting problems like in regulating the brake force distribution.